Welcome to this explainer. Look, if you're a chemical engineer, a process designer, or just someone fascinated by scaling up renewable energy, you know that maximizing plant efficiency is quite literally everything. But to truly optimize our reactors, we can't just look at the big picture. We have to get down to the molecular level and understand exactly what's happening to those chemical bonds. Today, we're bridging that gap between micro-level chemistry and macro-level plant efficiency.
Here is our roadmap for today. We'll kick things off with the circular bioeconomy target, move into the lignocellulosic triad, and then dig into thermal degradation mechanisms. After that, we'll contrast component behaviors, and finally bring it all together with reactor design and scale-up.
All right, Section 1, the circular bioeconomy target. Let's start with the big overarching objective driving all of these facility upgrades. Optimizing thermochemical conversion is the absolute linchpin for transforming raw, low-value biomass waste into high-value bioenergy. It doesn't matter if you're targeting solid biochar, liquid bio-oil, or syngas. Mastering these conversion pathways is exactly how we're going to hit those massive carbon-neutral and net-zero targets. We're essentially taking waste and making it the cornerstone of the circular economy.
But, there's always a catch, right? The main barrier to optimizing your plant's efficiency is that this feedstock is incredibly stubborn. Lignocellulosic biomass has an intrinsic recalcitrance. It naturally resists degradation. So to overcome that, we can't just treat biomass as a single uniform fuel source. We have to deeply understand how its individual chemical components behave under intense thermal stress.
That brings us to Section 2, the lignocellulosic triad. We need to dissect this feedstock into its three foundational pillars.
We are dealing with three completely different beasts here. First, you have straight, unbranched cellulose fibers. Then, you've got the highly branched, shorter side chains of hemicelluloses. And finally, wrapping the whole shebang together is a complex, hydrophobic, and highly aromatic lignin network. Because they are so structurally different at the molecular level, they behave entirely differently once they're inside a thermal reactor. Let's compare cellulose and hemicellulose for a second. Cellulose is this rigid, crystalline array of D-glucose units. That highly organized crystal structure gives it some serious thermal stability. Hemicellulose, well, it's entirely amorphous. It's a messy, irregular mix of different sugars like xylose, glucose, and mannose. Because it doesn't have that tight crystal structure, hemicellulose breaks down way earlier in your reactor.
So how does lignin fit into this? Lignin is a real game changer. It's an extensive, cross-linked aromatic polymer network with a massive molecular weight. We're talking anywhere from 2,000 to 7,000 grams per mole. That extensive aromatic network fundamentally alters your reactor dynamics. Those complex bonds require significantly higher temperatures to fully degrade and carbonize compared to the sugars we just talked about.
Let's dive deeper into the chemistry in Section 3, thermal degradation mechanisms. We're going to zoom in on the specific molecular bond dissociations that happen as things heat up. Let's break down hemicellulose first. It degrades in multiple stages. It kicks off with primary dehydration, right around 210 degrees Celsius, where you see a little bit of mass loss. Then comes the intense degradation, where the xylopyraneose chain actually depolymerizes. Finally, once you push past 340 degrees Celsius, you get volatilization, which produces various furan compounds. Now, these chemical pathways are highly specific. Cellulose decomposition, for instance, happens in a much tighter window. Say your reactor is targeting valuable anhydrous sugars like levoleucosen. To get that, your temperature profile has to tightly control the 300 to 400 degrees Celsius zone. That is the sweet spot where cellulose depolymerizes. If you overshoot or undershoot that window, your yield for those specific carbohydrate derivatives is going to completely plummet.
And hey, we aren't just guessing here. Spectroscopic data actually proves this out. X-ray diffraction, or XRD, lets us literally track the breakdown of cellulose crystallinity as temperatures rise. Meanwhile, FTIR, that's Fourier transform infrared spectroscopy, confirms the cleavage of specific bonds. For example, we can see the beta-glucosidic bonds in hemicellulose dropping off at just 220 degrees Celsius. We can watch these functional groups transform in real time.
Lignin's pathway, though, is entirely unique. Its ether and carbon-carbon bonds crack to form phenolic species and aromatic compounds. But here is the key difference. Unlike the sugars, which mostly volatilize and turn into vapor, lignin leads directly to the repolymerization of those monomers. They turn right back into solid aromatic char.
Because of these distinct stages, lignin has a massive degradation range. You get water evaporation early on, followed by primary decomposition spanning all the way from 250 up to 500 degrees Celsius. To get true carbonization, you have to exceed 500 degrees. So if you're trying to leverage high lignin feedstocks to make coal-like solid biofuels, you absolutely have to push your reactor well above 500 degrees to lock in that energy density.
Moving on to Section 4, contrasting component behaviors. Knowing the individual mechanisms is great, but we have to map how they all interact at the same time across the temperature gradient.
When you map the critical temperature thresholds, you clearly see a stagger. Hemicelluloses break first, starting as low as 180 degrees. Cellulose follows in a really narrow, intense window between roughly 315 and 400 degrees. And then there's lignin, acting like this robust backbone, requiring sustained heat and steadily breaking down all the way up to 800 degrees.
Thermodynamically speaking, this is make or break for your heat transfer calculations. The process actually shifts between an endothermic reaction, absorbing heat during cellulose degradation, and an exothermic reaction, where it releases heat during hemicellulose breakdown and later lignin carbonization. If you aren't actively modeling these exo and endothermic shifts, your reactor's thermal management is going to fail. Here's a tiny chemical detail that has a massive impact on your final product. Hemicellulose is primarily made of a pentose sugar called xylose. Because xylose lacks a hydroxyl group at its fifth carbon, it physically cannot undergo the dehydration needed to form anhydrous sugars like levoglucosan. Cellulose, being a hexose sugar, can. That one tiny structural difference completely changes your liquid bio-oil composition based on what you feed into the system. Because of all this, your feedstock selection strictly dictates your output. High cellulose feeds, they're going to maximize your liquid bio-oil yields, pushing nearly 67.5% at 500 degrees. But high lignin feeds will optimize solid biochar production. And crucially, that lignin-derived biochar has the highest heating value, or HHV, thanks to its incredibly dense, carbon-rich aromatic structure. All right, let's zoom back out for our final part, Section 5, Reactor Design and Scale-Up. Time to apply all this molecular insight to actual industrial plant operations.
So here is the ultimate question for any chemical engineer or plant manager. How exactly do you take these incredibly varied, overlapping thermal behaviors and translate them into a single, unified, scalable reactor design?
Well, it boils down to three engineering imperatives. First, you have to manage feedstock heterogeneity. You need to know the exact cellulose to lignin ratio of your input. Second, you have to account for complex heat and mass transfer limitations that get much harder as you scale up from the lab. And finally, you have to dynamically adjust your solid and vapor residence times to match whichever component's degradation profile gives you the yield you actually want. Because these molecular pathways constantly overlap and compete inside real biomass, your operational control levers are actually pretty tight. Precision control is everything. Managing your reactor's temperature profile, your heating rate, and your contact time. That is quite literally the only way to steer these competing chemical reactions and ensure your process stays reliable.
As we design the sustainable bioenergy systems of the future, I want you to think about this. By deeply understanding that triad of cellulose, hemicellulose, and lignin, and integrating these specific predictive models, how far can we push the thermodynamic limits? How close can we get to a genuinely carbon-neutral energy grid? Thanks for joining me on this explainer, and I hope this gave you a really powerful new lens for your next process design.